Okay. Welcome everyone. My name is Zoltán, and I'm a NetBSD developer. Before we start, I'd like to say a few words about myself. I've just started writing code for NetBSD like a year ago, so my commit writes are pretty new. And NPF was the first big project that I contributed to NetBSD. There's one other project pending that I talked about last year's BSD Day, but it's not finished yet. So, to talk about firewalls, we have to somehow define what a firewall is in the first place, right? So, the simplest view of a packet filter of a firewall is that it's a Boolean valid function. Because, you receive the packet, and you, based on whatever, you decide if you want to keep it, you want to drop it, or if you want to forward it to your application or other interface, or so whatever you want to do with it. And there are a few different implementations on how to decide in this situation. The first one is the Boolean expression tree. It works well. The only problem with it is just it's slow. This was the implementation used in early firewalls before the Berkeley Packet Filter in '91. So that was the original implementation. And then with the '91 paper on the Berkeley Packet Filter, they invented, or basically got a use for directed acyclic control flow graphs. Basically a graph where you only can move forward, not backward. So you get the packet and you start walking from the top of the graph to the end. And if you have an exit, if you can exit the graph somewhere, then you have a decision. But eventually you exit the graph because, as I said, you can't move backwards. And the third implementation is if you look at, for example, OpenBSD's PF, or it's used in many distributions, it's like a spaghetti code. So it's full of ifs, else. If anyone's interested after the talk, I can show you a TXT file from PF, which is basically like 400 lines of if-else structures. So it's horrible to maintain. And one of the questions I mostly got from people is, why the hell did you start to write a new firewall? Because, there's IP filter done by Darren Reed. The problem with IP filter is that OpenBSD removed it, Dragonfly removed it, and NetBSD still supports it, and so it's the default on Solaris, right? So it's somehow kept actively developed by Darren, or at least he promised he'll work on it from now on. And there's OpenBSD has PF, obviously, it's one of the oldest firewalls. FreeBSD has IPFV, because I have to admit I'm not familiar in depth with FreeBSD's firewall. So if any one of you is an IPFV developer, I'd love to chat. And then we have our own. And if you look at this list, it seems like every distribution has its own. And I have to assure you that we did not start to write NPF to have our own. So that wasn't the reason. The main reason, okay, so it's not listed, it's listed on the next slide, but the main reason we started to write it is because it was easier to rewrite the whole thing than just to keep supporting PF. Because PF's code base is not contained, it's not self-contained. Most of the new code, which goes even near around networking in OpenBSD, uses PF. So if you want to port it over to NetBSD, FreeBSD, whatever, you have to port that part too. And that's a very laborious task. So how did NPF start out? The NetBSD Foundations Board told on the lists that they would like to fund development for a new firewall because of the exact reasons. And Mindaugas applied and got the project funded by the board. He wrote the original code for NPF. And as you can see in the slides, it was imported last August into the core tree, into current. And the design was there already, but it lacked IPv6 support, and it still lacks some other features which we can explore during the talk. Now, we have IPv6 support now, but sadly there's still a big lock around our networking code. So even if the firewall is completely multi-threaded and scalable, the whole network stack is still logged by big lock. And the board, again, proposed to fund someone to rewrite the network stack in NetBSD to be more scalable and to revamp it, which is a huge work because you have to rewrite the interrupt handlers and restructure the code, make it modular, make it scalable with mostly low-class code. So it's a lot of work, and I don't know about application status. As you can see, the deadline was the last day of October, so we're going to see who applied. I haven't. So it's a really horrible task. So who sponsored the code? It was sponsored by Google. So I was a Google Summer of Code student this year too, and last year. Is there someone who's not familiar with Google Summer of Code? Or okay, everyone is great. So then you know how it works. Google gives you money, gives the students money. You do your code, and if everything goes well, you get $5,000, and the mentoring organization on project basis gets $500. So NetBSD had 9 projects this year, so we got some money to fund our development. And as you can see from the last point, I just committed the code yesterday around 2 a.m. into the current tree. It broke build, and I just fixed the build process like hours ago. Thank you. It was really a pretty exciting thing to break the networking code. So yeah. So let's see why in depth why we did this. So as I said, it was easier to just re-architect the whole thing because PF's there, but it's a spaghetti code. It's getting better and better. At least that's what Ryan promised me from BSD, but it's still a long way to go. And we needed some new features. It's 2011. And we don't want to see Flash players in Firefox and stuff like that. We want to see scalability. When you have lots of people use NetBSD for their routers, of course they use OpenBSD too. But sometimes, even if the OpenBSD people tell us that there's no such thing as a CPU bottleneck, there is. So if you have a lot of packets, depending on what kind of packets you have, you could hit a CPU bottleneck where you can't handle the packets with just one CPU. And because their code, it was designed for single-threadedness. And our code is designed for complete scalability. So it utilize as many cores as you have in your system, making it scalable. We have table support, which means basically that instead of hardwiring the IP addresses into the configuration, you can create a table, give it an ID, and just push the IPs into the table. And the firewall will look for the IPs in the table and decide if the packet is matching any IP from the table. It's a feature interesting. It's been available for PF for like 2-3 years now, but the Linux kernel just got it like 5 months ago. So in this regard, they were a bit behind. Of course, it's a stateful packet filter. No one can live without statefulness nowadays. We have the encode processor, which is, so as you'll see later from the concrete example, what we do basically is we run a VM inside the kernel. Because somehow you have to evaluate this control flow graph. And the most easiest way to do this is to compile your rule set into binary code. And you run this binary code in your own VM. So we have our own bytecode, we have our own VM in the kernel. It's pretty fast, and the bytecode engine's name is encode. So someone in the previous talk, when I did give this talk at EuroBSDCon, did not really understand what encode is, and I had to figure out from a blog post somewhere instead of asking me. So please ask if you don't understand any part, okay? So the encode engine is the bytecode engine running the actual configuration, evaluating the packets. So it's the implementation of the control flow graph. Well, apart from this bytecode engine, the other properties are hold for most firewalls, except they're not very modular. So let's say you run a gateway and you have SIP connections. You have network address translation and SIP connections. You have to support them. The easiest way to do this is to write a module just for SIP to extract the ports from the packet and put it in your state table. That's the simplest way to do it. But to do this on PF or to do this in IP filter, there wasn't an easy way to write modules to the firewall. Now with MPF, you can do this easily. Of course, it's portable, so you can just take the MPF source code from NetBSD, and you can integrate it with FreeBSD in a few hours, I guess, because the pfill hooks are there in FreeBSD. So if you want to do that, you can do it. Actually, FreeBSD's network stack is in a better shape than ours. So for benchmarking, I think I'll run NPF and FreeBSD kernel, at least, to do the actual firewall benchmarking. And Dragonfly BSD, since they dropped PF, they were looking for a new firewall, and they thinking of adapting MPF as their new firewall, as their base firewall. And NPF will be the base firewall in NetBSD 6 if it ever comes out. Okay, and please keep in mind that it's really a code under development, so there should be bugs. Okay, we're trying to be as bug-free as we can, but I'm pretty sure that there are some scenarios where what we did not think of. Okay, so how would you use it? So you install NetBSD, you build the current kernel, or you get NetBSD 6 if it comes out. You install it, and you want to start playing around with the firewall, right? So what would you have to do? You have to write a configuration file, which will look like something like this. So you write a configuration file. The syntax is pretty much like standard PF, with a few tricks. And then with mpfctl, you can compile this configuration to bytecode. Load it, and then you have the in-kernel VM evaluating the packet. Okay, the current parser is a pile of bugs. As just the parser, please keep in mind, okay? And it will be replaced by a new one by Martin. He's been promising it for like months, but it will happen eventually. Okay, so what can I do? We have real syntax that's similar to PF, so if you're migrating from PF or from any other firewall using PF syntax, most BSD firewalls do, then you'll have an easy time. It's not really a big task. We have group support, which means that you don't, let's say you have a router with 6 interfaces or with just 4 interfaces. You can group the interface together, give it a name, and specify your rules just on that interface. It makes your config much more readable than what you could write with the original PF syntax. Okay, we'll see an example in a sec. We have rules procedures, which means when you have a connection, not packets, you have to have a connection, like an active TCP connection or whatever. But when you have a connection, you can run procedures on it. You can write modules implementing your procedures, but the procedure is basically a packet transformation. So you could change, for example, the IP ID to be randomized in the headers. Or you could do logging or whatever I listed. And this is called sanitization in OpenBSD's PF. But you have the individual options here, and you can extend them as much as you'd like. Okay. We have table support, I already talked about that, and we have the application level gateways, which is basically the modules manipulating the state table for your applications. So for example, when you do a trace route, it usually needs an additional port. So if you if you filter out everything on the firewall, your system won't be trace routable. And I know many people who just drop everything in their firewall, and I think that's a good solution. But sometimes you have to allow additional things. And if you want to allow traceroute, either you open up the whole port range, which could be not exactly what you want, or you have to run some module handling traceroutes. And application level gateways are exactly these modules. As I said, they can do SIP, they can do RTCP, any other protocol you want. Okay, so let's have a detailed look in the config. So we have macro support, it's pretty standard. We define 2 interfaces, one internal, one external. We define a table, which is, we said it's a tree. So as you start adding IP addresses, it's built as a red-black tree. We have two procedures, one to log and one to randomize the ID. The log interface shows up as a real interface in the system, and you can TCP dump it, you can do anything you want on it to process the packet. And then, as you can see, we have the groups based on the interfaces. And there are plans to be able to specify not only the interface, but the packet direction. So if it's going in or out on the interface. And then you would have a better breakdown of the interfaces. So what it would do is we would block everything coming on an IP in the table. We would pass out every packet going out, but we would randomize their state, and we would keep their state. And we would log every SSH connection coming inside. On the internal group, we block everything coming in and everything out via low. Yeah, interesting. The block in all and the passing. Okay, yeah. So by default, we block everything, and if something comes on an IP in the table, then we allow that. Else we drop it and we allow everything outside. Okay. And the default group, what happens if you, let's say you have 3 interfaces and we just define two groups for 2 interfaces. So the third interface would be in the default group. Okay, you can do all the same rules in the groups as you'd like. Okay, so you've written the config, you used npfctl to compile it. Then what happens? How is it evaluated? So what we do is we have this bytecode engine inside the kernel. It has 4 registers, and it uses the standard word format. We have both CISC and RISC-like instructions. So we have instructions with fixed parameters, but we also use some commands with the load and store architecture. It's basically a mix, but it's very easy to expand. So if you look at the source, I think the engine source code is around 2,000 lines or something, which isn't that big. And the packets are processed as a byte stream. So we don't actually look at what's inside the packet. We only look at arithmetically on the packet data as the individual bytes. So we have commands on the byte engine as skip n bytes and compare n bytes. But everything is done in the 32-bit words. Okay? And one of the things, for example, so one of the things that the OpenBSD guys told me that they have cache trashing. If you have a large table, it can't fit in the CPU cache, and you keep filtering, then most of the CPU time is spent on updating the cache. Or, you know, you load something in the cache and you have to throw it out because it's irrelevant by the time you would use it. And for this reason, we traded some memory for CPU. So if you look at PF source code, they store the net masks not as the net mask value. For example, if you have a /24, we store only the value of 24. So that's a value. They expand it to 128 bits, as the full mask to do it. And this is something, if you have 1 million addresses, with this approach you can save some memory. Okay, but most importantly, you trade off memory for CPU time. So the exact balance of if you have, memory bandwidth, or if you have more CPU power, or whatever resource you have the most of, needs to be treated on an individual basis. So I plan to do this as an option, so you could change this in runtime. Because on some systems, one might perform better, and some systems the other. Okay, and we have our NPF ADDR structure, which is basically just a type def for IN6 address. Okay. So we do have a caching inside. We can keep everything in memory as much as we can. And we just, what we're trying to achieve is to have very efficient data structures, because we're thinking that's the key to have a very scalable code. we only have one lock around the tables in the whole core code. So we're operating locklessly in most of the code, which I think is pretty nice. So these are some information flags. This decides if your packet is an IPv4 or 6 packet, and if it was fragmented or not, and stuff like that. We have the source and destination IP. We store the size and the header length, because if you look at IPv6 headers, the header length is not something easy to calculate. You have to walk the packet. And we tend to do this very early in the code. So later, when you're running actually the graph, when you're evaluating the packet, you can refer to this data structure instead of, have to go back in the packet and read the value and use that. So this data structure is filled in before running the graph. And we have two unions to store the data, actual data. Okay, so let's look at the to-do list. As I said, it's a very new project. It has a long things to do. If someone wants to join, feel free. So we want to replace the red-black trees with Patricia and Radix trees. They have better performance. Actually, there's a paper published on Radix trees where you can have a lockless Radix tree. So it would be nice to use that. Then we would eliminate that single lock around the trees, which should give us some performance. And yeah, this is the trade-off I was talking about. So we could generate an array and prefill it with the actual 128-bit values of the net masks, and use that for lookups. This would give us a benefit and CPU time, but would trash the memory more. So it's trade-off. Yeah, so I'm coming from Linux world originally, and IP tables has really nice and detailed statistics. And I always found BSD firewalls lacking of statistics. What's going on? Which rule, which group has been hit the most? How much traffic went into that rule? You can't get this info from BSD firewalls. And I plan to do that with NPF. So we have per rule statistics with IP tables, because I really envied that feature. Okay. The other thing is, a friend told me about this in FreeBSD, for example. If you write a firewall, you have a firewall, set it up, and you load the firewall and change the IP address of one of the interfaces. The firewall won't follow the change. It will filter out anything. You have to reload the firewall to make it use the new address. It would be really nice if the kernel could keep track of the actual IP addresses of the interfaces, so you could add aliases and change the IPs as you want. Okay, we would like to control fragmentation on a per interface basis. This would be pretty nice, but it's not that easy to do. And yeah, two killer features. Everything is screaming for them. This is pretty new RFCs, so they came out in July. At least they were finalized in July, but I think they have pretty nice features. And of course, we have to write more documentation, because if you Google NPF, you won't find anything other than the mem page. I'm thinking that the mem page should be enough, really. But yeah, okay. So what we haven't covered in this short introduction to NPF is the performance aspect. As you can see, I have not presented any performance data. That's because we're still single logged outside of the firewall in the network stack. And until that's gone, I can't present you with real data. And we haven't talked about packet sniffing. Packet sniffing is a favorite area of mine, and I really think with NPF's lockless code and the clever use of mbuffs, we could use some packet sniffer implementation with NPF. So we'll see. And we want to do the sniff list on slides. We want to do the traffic shaping too, because we envy that from PF too. Okay. So, any questions? Because we have a few minutes. Okay.
So, you mentioned modularity. And application layer gateways. Do your application layer gateways run in the in kernel space or in user space?
They are running in kernel space. Okay. So you have to load them as a module.
Okay, that's good. And do you need to reassemble to run your ALGs, or can you just track the mbuff? Because in PF, the helper is running user space, which is a design decision, but that means you need to reassemble your fragment until you have all the information you need, which is slow.
Yeah, the ALGs have direct access to the graph, and they have direct access to the state table.
And they see the mbuff as well, so you don't need to...
You don't need to do anything. You can load them and remove them whenever you want.
All right.
Yeah, it's pretty
And
cool.
can your ALGs run in parallel, or...
Yeah, you can have...
your whole network stack is still locked under a single lock, but can you run your ALGs in parallel?
Currently they are evaluated not in parallel, but in sequential order. But I don't see any reason why they couldn't be.
Well, it depends. If you're going to rewrite a packet, you don't want two ALGs rewriting the same packet.
Yeah, sure.
You need to do some scoring.
Somehow the user would have to make an order of the ALGs, I guess. With that ordering, you could do parallel processing.
All right.
Yeah.
Sounds good. Improvement over PF.
Yeah. So any other questions?
Do you have questions? Do you think you will be ready with NetBSD 6 with your basic work?
Definitely. It will be the default firewall. So, yeah. Okay. So
any other questions?
No. So thank you, everyone.
Yeah. Thank you very much.